Thermodynamics is a branch of physics that deals with the relationships between heat, work, and energy. It is a fascinating field that governs the behavior of energy and matter in our universe. The word thermodynamics originates from the Greek words therm, heat, and dynamis, power, highlighting its focus on heat and energy interactions. One of the fundamental principles in thermodynamics is the conservation of energy, as stated in the first law of thermodynamics. This law asserts that energy cannot be created or destroyed, only transformed from one form to another. It is remarkable to think that the energy we use in our daily lives follows this universal law, whether it's the electricity powering our devices or the fuel in our vehicles. The second law of thermodynamics introduces the concept of entropy, which quantifies the disorder or randomness in a system. This law dictates that natural processes tend to increase the overall entropy of the universe, leading to a directionality in energy transformations. For instance, the heat transfer from a hot cup of coffee to the surrounding air follows the principles of the second law. Understanding thermodynamics allows us to optimize energy conversion processes for improved efficiency. In fact, the efficiency of engines, refrigerators, and other devices is governed by thermodynamic principles. It is astonishing to realize that even the climate system operates based on thermodynamic principles, with energy exchanges driving weather patterns and climate change. By delving into the realm of thermodynamics, we gain insights into the fundamental laws that govern energy and matter, shaping our everyday experiences and the world around us. The first law of thermodynamics, also known as the law of energy conservation, is a fundamental principle that governs the flow of energy in our universe. It states that energy cannot be created or destroyed, only transformed from one form to another. This law provides a crucial foundation for understanding the behavior of energy in various systems, from the smallest particles to the vast cosmos. One interesting aspect of the first law is its application in the field of bioenergetics, which studies how living organisms convert and utilize energy. For example, the human body is a remarkable energy converter, with the average adult converting around 2,000 to 2,500 kilocalories of food energy per day into the energy needed for daily activities. This energy conversion process follows the principles of the first law, ensuring that the total energy input equals the energy output. In the realm of physics, the first law of thermodynamics plays a crucial role in understanding the behavior of gases. For instance, when a gas undergoes an adiabatic process, no heat exchange with the surroundings, the internal energy of the gas remains constant, showcasing the conservation of energy. The first law also finds applications in the field of environmental science, particularly in studying energy flows within ecosystems. By analyzing energy inputs and outputs in ecosystems, scientists can gain insights into the efficiency of energy transfer and the overall stability of the ecosystem. One fascinating example of the first law in action is the energy balance of Earth's climate system. The incoming solar radiation provides the energy input, which is balanced by the outgoing thermal radiation emitted by the Earth. This delicate energy balance is essential for maintaining the Earth's temperature within a habitable range. In the context of engineering, the first law of thermodynamics is a cornerstone principle for designing energy systems with high efficiency. For instance, in the design of heat engines, such as steam turbines or internal combustion engines, engineers strive to maximize the conversion of heat energy into mechanical work while minimizing energy losses. Achieving high efficiency in energy conversion processes not only conserves resources but also reduces environmental impacts. The first law of thermodynamics underscores the interconnectedness of energy transformations in our world, highlighting the universal principle of energy conservation that governs all natural processes. By embracing this law, we can unlock new possibilities for sustainable energy utilization and technological advancements that benefit society and the environment. In everyday life, the first law of thermodynamics manifests in numerous intriguing ways, showcasing the conservation of energy principle. Consider the process of boiling water on a stovetop. As the water absorbs heat from the stove, its temperature rises until it reaches the boiling point. At this stage, the energy input is utilized to break the intermolecular bonds within the water molecules, transitioning them from a liquid to a gaseous state. Despite the visible transformation from liquid to steam, the total energy within the system remains constant, in accordance with the first law. Another common example is the operation of a refrigerator. Refrigerators work by removing heat from the interior compartments and releasing it outside, thereby maintaining a cool temperature inside. The energy consumed by the refrigerator is used to transfer heat from a lower temperature inside the fridge to a higher temperature outside the fridge, ensuring that the total energy remains conserved. Interestingly, the human body also abides by the first law of thermodynamics. When we consume food, our bodies extract energy from the nutrients through metabolic processes to fuel various bodily functions. The energy obtained from food is utilized for activities such as walking, talking, and even thinking. Remarkably, the total energy input from food is balanced by the energy expended by the body, illustrating the energy conservation principle in action. These examples highlight how the first law of thermodynamics governs energy transformations in our daily experiences, emphasizing the universal nature of energy conservation. The second law of thermodynamics introduces the concept of entropy, which is a measure of the disorder or randomness in a system. This law states that in any energy transfer or transformation, the overall entropy of a closed system will always increase over time. One interesting implication of the second law is the idea of irreversibility in natural processes. For example, when an ice cube melts in a warm room, the entropy of the system increases as the orderly structure of the ice gives way to the more disordered liquid water. This irreversible change aligns with the second law's prediction of increasing entropy. Another fascinating aspect of the second law is its connection to the arrow of time. While the fundamental laws of physics are time reversible, the increase in entropy over time provides a directionality to processes, distinguishing between past and future. This asymmetry in entropy growth is a key feature of the second law that shapes our understanding of the universe. In statistical mechanics, entropy is quantified as a measure of the number of possible microscopic configurations that correspond to a macroscopic state. This statistical interpretation of entropy provides a deeper insight into the probabilistic nature of thermodynamic systems. One intriguing statistic related to entropy is Boltzmann's formula, which relates entropy to the number of microstates in a system. The formula S equals K ln W, where S is entropy, K is the Boltzmann constant, and W is the number of microstates, highlights the statistical foundation of entropy. The second law of thermodynamics also plays a crucial role in the efficiency of energy conversion processes. For instance, in heat engines, such as steam turbines, the second law sets limits on the maximum efficiency that can be achieved. The Carnot efficiency, derived from the principles of the second law, provides a theoretical upper bound on the efficiency of heat engines operating between two temperature reservoirs. Understanding and applying the second law of thermodynamics is essential for optimizing energy systems and processes to minimize energy losses and enhance overall efficiency. The second law of thermodynamics, with its focus on entropy increase, has intriguing applications in daily activities that showcase the natural tendency towards disorder. One fascinating example is the process of mixing cream into coffee. When cream is poured into hot coffee, it quickly disperses and mixes due to the random motion of molecules, leading to an increase in entropy. This spontaneous mixing is a manifestation of the second law in action, as the system moves towards a higher entropy state. Another interesting application can be seen in the diffusion of perfume in a room. When perfume is sprayed, the aromatic molecules disperse and fill the space, gradually spreading out evenly. This diffusion process follows the direction of increasing entropy as the initially concentrated perfume molecules spread out to achieve a more disordered distribution. In the realm of food and cooking, the second law influences processes such as baking. When a cake is placed in a preheated oven, the heat causes the batter to rise and expand, leading to a transformation from a dense mixture to a fluffy cake. This expansion and rise in volume correspond to an increase in entropy, as the cake batter undergoes a spontaneous change towards a more disordered state. Interestingly, Statistics related to entropy growth provide insights into the probabilistic nature of thermodynamic systems. The Boltzmann formula, which relates entropy to the number of microstates, highlights the statistical foundation of entropy and its role in quantifying disorder. These daily examples and statistical interpretations underscore the pervasive influence of the second law of thermodynamics in shaping our experiences and understanding of energy transformations. Entropy is a concept in thermodynamics that quantifies the degree of disorder or randomness in a system. It plays a crucial role in understanding the directionality of natural processes and the limitations imposed by the second law of thermodynamics. One fascinating aspect of entropy is its connection to information theory. In the field of information theory, entropy is used to measure the uncertainty or randomness in a message or data set. The concept of entropy in information theory was introduced by Claude Shannon, who defined entropy as the average amount of information produced by a random variable. This link between thermodynamic entropy and information entropy highlights the interdisciplinary nature of entropy as a fundamental concept in diverse fields. In statistical mechanics, entropy is related to the number of microscopic configurations that correspond to a macroscopic state. This statistical interpretation of entropy provides a deeper understanding of the probabilistic nature of thermodynamic systems. Boltzmann's formula, S equals K ln W, where S is entropy, K is the Boltzmann constant, and W is the number of microstates, quantifies the relationship between entropy and the multiplicity of states in a system. This formula underscores the statistical foundation of entropy and its relevance in characterizing the disorder in a system. Entropy also plays a crucial role in the context of energy dispersal and heat transfer. The spontaneous flow of heat from a hot object to a cold object follows the direction of increasing entropy, as energy tends to disperse and equalize throughout a system. Understanding the concept of entropy provides insights into the natural tendency towards disorder and the constraints imposed by the second law of thermodynamics. Heat transfer mechanisms play a vital role in various natural and engineered systems, facilitating the movement of thermal energy from one location to another. One intriguing mechanism of heat transfer is conduction, which occurs through direct contact between materials. For example, when a metal spoon is placed in a hot cup of tea, heat is transferred from the tea to the spoon through conduction, causing the spoon to warm up. Another fascinating heat transfer mechanism is convection, which involves the movement of fluids or gases to distribute heat. In a pot of boiling water, convection currents form as hot water rises and cooler water sinks, creating a continuous circulation that helps in even heating. Radiative heat transfer, on the other hand, occurs through electromagnetic waves and does not require a medium for propagation. An interesting fact is that the sun primarily heats the Earth through radiative heat transfer, with solar radiation traveling through the vacuum of space to reach our planet. In terms of numbers, the Earth receives approximately 174 petawatts of solar radiation, highlighting the immense energy transfer involved in this process. Understanding these heat transfer mechanisms is essential for optimizing energy systems and designing efficient technologies. For instance, in thermal insulation, minimizing heat transfer through conduction and convection helps in maintaining desired temperatures and reducing energy losses. By harnessing the principles of heat transfer, we can enhance the efficiency of heating and cooling systems, improve energy conservation, and advance technological innovations for a sustainable future. Efficiency in energy conversion is a critical aspect of optimizing energy systems and reducing wastage. One fascinating example of energy conversion efficiency is found in traditional incandescent light bulbs, where only about 5% of the electrical energy is converted into visible light, while the rest is dissipated as heat. In contrast, modern LED light bulbs are much more efficient, converting around 80% of the electrical energy into light. This significant improvement in efficiency has led to widespread adoption of LED lighting for its energy-saving benefits. Another interesting fact is that the average efficiency of gasoline-powered internal combustion engines used in vehicles is only around 20%, meaning that 80% of the energy from gasoline is lost as heat. This inefficiency has driven research into alternative propulsion technologies, such as electric vehicles, which can achieve efficiencies of over 80%. In the realm of renewable energy, solar photovoltaic (PV) panels have an efficiency range of 15 to 25%, with some advanced technologies reaching efficiencies above 40%. Improving the efficiency of solar panels is crucial for maximizing the conversion of sunlight into electricity and making solar energy more cost-effective. The concept of energy conversion efficiency is quantified by the efficiency formula, which is the ratio of useful output energy to input energy. For example, the efficiency of a heat engine is determined by the ratio of the work output to the heat input. By enhancing the efficiency of energy conversion processes, we can reduce energy consumption, lower greenhouse gas emissions, and enhance sustainability in our energy systems. Thermodynamics plays a crucial role in understanding climate change dynamics. For instance, the Earth's energy balance is influenced by the absorption of solar radiation and the emission of thermal radiation. Interestingly, the Earth receives about 174 petawatts of solar radiation, with only a fraction being absorbed by the atmosphere and surface. This energy imbalance drives climate processes, including temperature variations and weather patterns. The greenhouse effect, a phenomenon where certain gases trap heat in the Earth's atmosphere, is a key aspect of climate change. Carbon dioxide, a greenhouse gas, contributes significantly to global warming by absorbing and re-emitting thermal radiation. The efficiency of energy conversion in natural processes, such as photosynthesis in plants, also impacts the carbon cycle and climate regulation. Understanding the thermodynamic principles underlying climate change is essential for developing sustainable solutions to mitigate its effects. Did you know that the efficiency of LED light bulbs can reach up to 80%, making them a highly energy-efficient lighting option? In contrast, traditional incandescent bulbs are much less efficient, converting only around 5% of electrical energy into light. Another interesting fact is that electric vehicles can achieve efficiencies of over 80%, surpassing the efficiency of gasoline-powered internal combustion engines. When it comes to solar energy, some advanced photovoltaic panels can reach efficiencies above 40%, showcasing the potential for harnessing solar power more effectively. The Earth's energy balance is influenced by the absorption of solar radiation, with the planet receiving approximately 174 petawatts of solar energy. These intriguing details highlight the importance of energy efficiency and thermodynamic principles in addressing climate change challenges.